Welcome back, everybody, and welcome to this session on the particle Hall formalism and the transition to our first encounter with many-body methods. And one of these methods is called configuration interaction theory. And some of you are actually working explicitly with these models in either your PhD or master thesis. So we are going to today to revisit some of the particle Hall formalism. And then I'm also going to link this with one of the exercises. And then we are going to simplify a little bit this particle Hall formalism. But let me quickly remind you of what we did last week. So we had let me just bring this up here. So these are the topics for this week. So we're going to have a discussion of the particle Hall formalism with examples and diagrammatic representation. And then this will serve as an entry point to full configuration interaction theory. And on Friday, this is the main topic for the lecture. The material is covered pretty well by these chapters 3 and 4. Chapter 3 and 4, Shavit and Bartlett, does not cover full configuration interaction theory. So the slide material is what we'll cover, that material. And then there's a 5th exercise set as well. So the topic which we began with was simply a redefinition. So let me just bring this back of creation and annihilation operators. And what we defined then was an operator that in case we are acting on a vacuum state, this C here, or phi 0 as we called it, this new reference state is so that that operator is going to give us 0. We have the same kind of anti-commutation rules, except that now we have assumed a different contraction between two operators, a creation and annihilation operator. So the physical interpretation of these operators is normally that of so-called quasi-particle states, in the sense that we can create a one particle, one hole excitation. So they are normally called quasi-particle states. So that means that a state defined by the addition of one extra particle to the reference state may not necessarily be interpreted as one particle coupled to a core. So we defined a new creation operators, which were defined like this. So sometimes you will see this notation with an alpha minus, but we did not end up using that notation. So today I'm just going to bring up the more compact notation, which we will use throughout the semester. So in the original articles, people would then distinguish between these actions of the operator in this vacuum state. This is a new reference state, where you now have, in case the state alpha is not included in C, then we create a new state with n plus 1 particles. In case alpha is included in C, then we destroy one particle, we just take it out. So we have an n minus 1 system. So what we are saying then, loosely, as a kind of jargon, when alpha is above the Fermi level, we create a so-called particle state. Whereas when alpha is below the Fermi level, we remove a particle and we say that we create a whole state. And that's why we keep this creation operator symbol for that operator beta alpha. Now, this becomes a little bit more cumbersome when we are dealing with calculations of different expectation values. So what we often end up doing then is simply to keep the original operators, but then we specify whether this is a state above or below the Fermi level. And that brings in a much more compact notation and easier to use formalism. But you will encounter in many textbooks people who consequently use this particle Hall formalism. So for some of you doing nuclear physics, there's a very good textbook on the nuclear many-body problem by Jouni Suhonen. You may have seen that book. That's a very good book, actually. Highly recommended. And Jouni keeps consistently this type of formalism. Whereas in most many-body texts, this is normally abandoned and replaced by a simpler way of doing it. So this would be the way you would define these operators when you are defining also an annihilation operator. So above the Fermi level, you actually destroy a particle in a state alpha, you just remove it. So that brings you back to an n particle state. Whereas if you are below the Fermi level, then you're actually creating a state which now has a single particle in the quantum numbers alpha. Then you can then look at the operations on a given state. So this is a kind of formalism which some of you have encountered in the textbook by Jouni Suhonen on the nuclear shell model and nuclear many-body problem. And in that specific case, you would see a state being labeled in this way here, where you now create a number of states below the Fermi level, and then you create a number of states above the Fermi level. So one of the things which we did was then to rewrite the operators in this new formalism. And one of the simpler operators is actually the number operator. And you can then show that this can be rewritten when we write it in a normal ordered form in terms of a sum over states larger than the Fermi level and states below, which we loosely call for whole states. So we would typically call states, even if they're occupied, we will call them for whole state below the Fermi level and particle states above. So this has become part of the jargon. Even if you, so what you would say then is that this vacuum state, which is filled up to a certain level with all single particle states being occupied, we would typically call these states whole states, even though they are occupied. So it becomes a kind of jargon in the way you speak about specific states. Now, you can rewrite this, and we did that exercise last week. And one of the other things which we did was to rewrite the one-body operator. So we got these different terms. And this term which you see here is a term which then is the expectation value of the vacuum or the new vacuum to the new vacuum expectation value for the unperturbed part of the Hamiltonian. And this translates often into what we normally call the non-interacting or the unperturbed single particle energies. In case this basis alpha is an eigenbasis of H0. Now, what we have in this case is these new operators where we have defined which states are above and below the Fermi level. And we have one contribution, which is just a constant, which refers to a vacuum expectation value. And then we have what we last week rewrote in terms of a normal ordered set of operators, because you see now that we have the creation operators to the left and we have the annihilation operators to the right. So we would say that these are the standard normal ordered form of a second quantized operator. Now, these equations becomes a little bit unwieldy and cumbersome to use, and we are going to make it a little bit more compact. So one of the other things which you will see, and this is just an exercise which is not perhaps the most exciting thing to do, but you can take a one-body or two-body operator now and just rewrite it, where what we have done now is to define, as we did last week, and I'm going to repeat this one, letters A, B, C, D to indicate states above the Fermi level. So this would only be states above, particle states, as we call them, loosely. So you can rewrite it in terms of that. And then we have the terms I, which are states below the Fermi level. So that would be a so-called whole state. And we can rewrite the second term in terms of this normal ordered operators. We can then take the third term, which now involves a double sum over particle states and two whole states. And you will get this expression here. So I'm just giving you the expression. This is a kind of exercise where you just reorganize the operators. And then you use the anti-commutation rules to rewrite everything in terms of normal ordered chains of operators. So this is actually, I don't give this as an exercise anymore because it's not very exciting to do that. And I will show you today, in connection with the exercises this week, an easier way of calculating the same expressions. So there's a fourth term, where you now have 3 such creation operators and 3 such annihilation operators. This is also normal order. And then there's a final term where we have only sums over states below the Fermi level. And then there is a constant term here, which refers to the term which we got from the vacuum to vacuum expectation value. Now, what we are going to do now, when we switch over to the whiteboard, is just to remind ourselves about that new labeling which we introduced last week. So let's bring up the whiteboard immediately. And then remind ourselves about the kind of labeling which we are going to use. So we are trying all the time to compactify the equations. That's the main message here. So the labeling which we introduced last week is a specific one which is much used in quantum chemistry. It has also been used partly in nuclear physics, but less in condensed matter physics. But this is just a labeling which is convenient. So we would have the Fermi level here, and then we are having all the states below the Fermi level. And in this particular case, we are going to label these states. So there will be an epsilon 0, epsilon 1. These are the energies. And then we have an epsilon n minus 1, epsilon n plus 1. Now, these states are going to just get a label like I, J, K, L. And then we have the states above the Fermi level. So this is n here. Let me just correct that one. This is n. And then we have a new state, n plus 1. And then we have an epsilon n plus 2. So I'm just putting in the energies here. And then we obviously make a truncation with a little n. But in principles, as we've been saying many, many times now, this number of single particle states is infinitely large. So just think of the harmonic oscillator. You have an infinite set of basis states. And now these states are going to get the labels A, B, C, D, etc. And then we are going to have a common denominator for all these states, where we use the subscripts P, Q, R, S, etc. And we will loosely call these states for whole states. And we are going to call these for particle states. And the whole idea is that by introducing a new reference vacuum, the hope is that that can simplify the calculations of quantum mechanical expectation values of systems with many particles. So for those of you who are familiar with condensed matter physics, this type of possible states where you can excite this one up to a new state, these are called excitons in condensed matter physics. We will often call them for just particle hole states, so particle hole excitations. So that's a kind of jargon which we develop in order to describe physical states in the system within the orthonormal basis which we are using. That orthonormal basis may not be a good representation of physical reality. So what is physical reality and how we interpret that one is just obviously another topic. So what we have then is that these operators have now specific contraction rules. So when we looked at the operators previously with respect to the true vacuum, then there was only one contraction which was non-zero. But now we are going to have to redefine it, since we are going to keep the old labels, the old creation and annihilation operators. So this is going to be equal to delta PQ if P and Q are larger than the Fermi level or above the Fermi level. So if you see something like AA and AB dagger, this is actually equal to delta AB. And if I try to do AA dagger of AB, this contraction, this is automatically equal to 0, according to our traditional rules, the standard rules which we introduced before. Then what we have is that this AP, which this specific contraction which you see here, which was 0 with respect to the true vacuum, is now non-zero in case delta P and Q are states below the Fermi level. So that means that if you see something like an A dagger, AJ, this contraction here, this is actually equal to delta IJ. So instead of having explicitly different operators for these specific states, as also Shavit and Bartlett do in their textbook, we are simply going to use the standard operators. And just to quickly remind you of some of the applications of these definitions, is that if I now have something like this, so if I have a state, this is the vacuum state, phi 0, the reference vacuum, that corresponds to all states above, below the Fermi level, which are being filled up by different particle states. So this state here, if I now have an A acting on phi 0, this is obviously equal to 0, because A is not included in phi 0. So this is a state above the Fermi level, and we cannot destroy a state above the Fermi level which is not included in this reference state. So if I, on the other hand, act with this one on phi 0, this is going to be given by something which we will label as a phi of A. So that is actually equal, if we now do the setup of the original state, if we now define this phi 0 to be given by an A1, A2, up to AN. So this is our new reference vacuum. That means that this new state, phi of A, is going to be equal to AA dagger, and then we have this other chain of operators, A2 dagger up to AN. And this is then rewritten in terms of a ordering which we have chosen, so that A1, because we're assuming now that A is on top of N. Like that. So this becomes an N plus 1 state. So an N plus 1 particle state. The previous one is just an N particle state. Okay. Then we have the action of AI on phi 0. And here the assumption is that this state I is actually included in phi 0. So this means that we are actually removing a particle in a single particle state I. And this would be given by minus I, minus 1, where we just remove the state I, and then we have to perform the permutations of all these different operators. And then we would have an A1 dagger, A2 dagger, and then we have an AI minus 1 dagger, and then I have an AI plus 1 dagger, and this goes all the way up to an AN dagger acting on the true vacuum. So this is an N minus 1 particle state. And then I have the next operation. If I try to do this, then this has to be equal to 0, because I is already included. So I cannot have more than one particle in a single particle state. So this is then by definition 0. So these are the new rules which we have with respect to the new vacuum. And the thing which I'm doing now for simplicity is simply just to include this new notation with I, J, K, etc. being states below the Fermi level, and A, B, C, D being states above the Fermi level. So that means that the state which now contains a operation like this AI and AA dagger A and AI acting on phi 0. This is something which we would label as an I here, a subscript, to indicate that this is a one particle, one whole state. So what it means in our picture up to the Fermi level, so we have a set of single particle states, and this is state I, and now we move this particle up to a state which we call A here, and we label this as a one particle, one whole excitation. And then last week we discussed two particle, two whole, we can have three particle, three whole, etc., etc. One of the reasons why I bring it up again is that we are going to use this notation when we are going to introduce the full configuration interaction theory. Because then excitations about the ground states will now be interpreted in terms of these particle whole excitations. But you're not limited to that, because you could think of having a system where you have states up to a given Fermi level, which would then define a core. But then you can keep adding particles to that. So if you're looking at an atom like neutral aluminum, you can think of that as 2 electrons on top of neon 10, on neon, which has 10 electrons. So you could think of neon then, neutral atomic neon, as a core, and then you add electrons on top of that. So 2 electrons would then be a system which could be used as an ansatz for aluminum, which has 12 electrons, if I don't remember wrongly. You can go to nuclear physics, and you can think of a nucleus like oxygen 18, where you can have oxygen 16 as a core, and that defines the Fermi level. And then you can have 2 neutrons on top of that, and that would be a model for oxygen 18. Because oxygen 16 has 8 protons and 8 neutrons, and oxygen 18 has 10 neutrons and 8 protons. So these are just the kind of ways by which you now can start thinking of using this formalism to make ansatzes for a complicated many-body system. And it gives you a language which is very handy in describing these systems. So just to try to exemplify that, so if you think of a nucleus like oxygen 18, which for those of you who are not fully familiar with nuclear physics, this is a system which has 8 protons and 10 neutrons. And the way you would define this system, you can idealize this system, is now to define a Fermi level for a core. So this would be oxygen 16 plus 2 neutrons. And I'm going to put this N here, which is not this limit of single particle states, but it's actually the number of neutrons which I have. So you could now think of a Fermi level which contains 8 single particle states here for the proton degrees of freedom. So there are 8 in total, and these states are filled up with 8 protons, and then you have a similar set of single particle states, 8 in total, where you have the neutrons, and 8. So this could be this system here, which you would typically call for a core, or an ansatz for a Fermi vacuum. So you can think of this now as an ansatz for oxygen 16. So what you see here would now be my system, which I call phi 0. Then, with this creation and annihilation operators, I can add particles to this system. So if I look at the number of single particle states here, I have an infinity of such states. And now I can think of adding 1 more neutron, which would be oxygen 17. And I can add 2 more neutrons. And this would now be a model for oxygen 18, which I write in a sloppy way like this, which could now be given by A of A beta multiplied with this core, which is oxygen 16. So this is my oxygen 16 core. So I add 2 neutrons on top of oxygen 16. I can do exactly the same in atomic physics. I can do the same in molecular physics. And also if you're looking at the systems in condensed matter physics like quantum dots, which are kind of artificial atoms, I can use very much the same kind of labeling on states which are constructed by adding 1 particle or 2 particles and so on top of what you call a core. So in nuclear physics, for instance, this model here has been extremely successful in describing experimental data. And that's why we think that this theoretical way of modeling the states makes sense. It gives actually a very good description of many experimental data. So these are typical ways by which we can use these type of, this type of formalism. You can stay within oxygen 16 because oxygen 18 is an 18 particle system. But if I don't want to do oxygen 18, I can look at excitations around the Fermi level for oxygen 16. And in nuclear physics, there are some very important excitations which make life difficult for people doing configuration interaction theory. And these are alpha particle excitations. So I can actually have a 4-particle, 4-hole excitation in oxygen 16, which is actually the first excited state in oxygen 16. And that complicates life because then I have to excite 2 protons and 2 neutrons. And that is normally called an alpha particle excitation. So the interesting thing with many of these systems is that often you have this kind of macroscopic, microscopic way of thinking. And some of the states, you can actually see that if you look at the spatial distributions of protons and neutrons, that some of these excited states actually look like an alpha particle excitation. So you would have the alpha particle, you can actually interpret this type of excitations as 4 alpha particles with different spatial distributions. That's quite interesting. That gives another model for the same system. Okay, that was just a digression. And since we have many nuclear physics aficionados here, I thought of just using that as an example of a system. So what we are going to look at now is the way we can rewrite operators. And this goes back a little bit to the exercises this week. So I said that we have these contractions now, so when we have the state phi 0, the new vacuum, and if I have this one, this contraction here, this is equal to delta PQ. So let's just quickly remind ourselves about that one. If P and Q are larger than the Fermi level, and phi 0 of AP dagger AQ, this contraction here, and that is equal to delta PQ if P and Q are less than the Fermi level. So let's now look at the operators which we have and try to see how we can now rewrite the operators in terms of the new vacuum expectation value. And we have a general operator, PQ, which we rewrote in terms of these operators, B. But what we know now is that if we look at these operators and think of these in terms of explicit contractions which we make, so just think of Wick's theorem. So if you now look at the operators, so there's often something which confuses people when you look at these operators, because the expressions which are coming now are actually us thinking of this operator acting on a state, and we're looking at an expectation value of a vacuum to vacuum expectation value. So this operator here, we know that that can be rewritten as a normal ordered operator. So it means that we can actually rewrite it, PQ, and we have a normal ordering with respect to the new vacuum. which we indicated last time like this. So this is a normal ordered operator, and this is acting on the vacuum state, and the operations which we have then when we act on a vacuum state have to follow these kind of rules which we have defined here. But then what we have next is a term where we have PQ, and now we have performed the contraction, and this contraction is given by P of H0 of Q, and then I have a delta PQ, and where these guys have to be elements of states below the Fermi level. So the label I is now a state below the Fermi level. So, and this simply follows from us using the contraction, the anti-commutation rule. So this AP, AQ plus AQ, AP dagger is equal to delta PQ. Now, when I have the operator in this specific form, and I'm performing the contraction here, then the only non-zero vacuum-to-vacuum expectation value is given by states below the Fermi level. So what we found last time, when we used these operators B, is that we could rewrite this as the following. So we have the sum over P and Q. This is the general normal ordered operator with respect to the new vacuum of AP dagger AQ plus this sum over states below the Fermi level. And from now on, I'm going to skip this symbol F. I'm just going to write I, because these are states below the Fermi level. So I'm summing over all the states below the Fermi level. And this is given by I of H0 of I. And we just leave it like this, because this may just give us an epsilon of I, in case I is an eigenbasis of H0, but else we can just leave it as it stands here. So this last term, which we have here, this term was nothing but H0 and its expectation value with the non-interacting part of the Hamiltonian, or the H0 part of the Hamiltonian, which is normally a part of the Hamiltonian where we can find analytical solution, which means then that this phi 0 is an eigenbasis of the many-body operator H0, which is normally a sum of one-body operators. Now, if we now look at a general two-body operator, so this HI here, so let's take a look at that one. So we have a sum of a PQRS, and we have written it in this form, in a very general form, like this. And these matrix elements are now anti-symmetrized. And I will also, for simplicity, just skip the AS sign from now on. So the numerical number 1 divided by 4 indicates whether this is an anti-symmetrized matrix element or not. And then what I have is the creation and annihilation operators like this. Now, if I now think of Wick's, using Wick's theorem, and I'm normal ordering this operation on a vacuum state, I'm calculating the vacuum-to-vacuum expectation value of this quantity. Then we know from Wick's theorem that if we now take this operator chain, so AQ, AS, AR, there is a normal ordering. So I'm using these signs here to indicate that this is a normal ordering with respect to the new vacuum. So this symbol, this curly parenthesis, so this is normal ordering, and I'm using Wick's theorem with respect to new vacuum, to new reference state. phi 0. So if you think back to Wick's theorem, we have one normal order product of operators, and then we have the normal ordering of all possible contractions between one set of annihilation and creation operators. So there's going to be a new normal order term where we have AP dagger, AQ, AS, AR. And now we are looking at the possibilities of having one contraction only. So this term which you see here, the only possibility which you have here is actually a delta QS, where these states have to be below the Fermi level. That's the only contraction which is possible. Then I will have an AP dagger, AQ dagger. So we are getting a chain of such contractions. So the next possibility is actually this one. In this case, I'm going to get a minus because I have to interchange S and Q. So I'm going to get a delta P of S, where they also have to be below the Fermi level. And then you see that you have two more here. So let's add all of them for the sake of completeness. And then we have an AP, AQ, AS, AR. And now we can take, if you look at what we had here, we can now take this contraction. And then finally, we have an AP dagger, AQ, AS, AR. This one. These are the only non-zero ones, because when we take contractions between creation and or annihilation, that is exactly equal to 0. And finally, we have the term using Wick's theorem, where we now have two pairs of operators being contracted. So we have this possibility. And finally, we have the last possibility here. Which will be this one. And that gives us a minus sign when we look at the contractions. So when I sum up everything here, all the Kronecker deltas which I get, I'm going to have one term, which is now the normal order term. So that means that if I do that, then my H of I piece will now contain 1 divided by 4 of PQRS. And then I have PQ, VRS, and I'm skipping the AS symbol. And I'm using this new notation, which I will drop afterwards. So it's pretty common just to leave it out. But now I'm just indicating that these are normal ordered operators with respect to a new vacuum or new reference state. So that's one term. Now, if I look at all these one contraction guys, so what I'm going to be left with is now two operators, an AP dagger here and an AR. And this is going to give me a matrix element. So what I'm going to have is something like this, plus 1 divided by 4. There is a sum over P and R in this case, and Q as well. So when we now look at the contractions, so Q and S have to be equal to I. So that means that this double sum disappears, and I'm just left with a one summation over I. And then I have P and S. So the first term here gives me, since I have P and R, so I have a sum over PR, and then a summation over I. So one of the double sum disappears because I have a Kronecker delta between Q and S. So what I end up with then is a matrix element of this type here. So it's going to be a P, and then I have an I, a V, an R, and I. This matrix element is anti-symmetrized. And then I have a normal ordered one particle operator, which is now given by P and R. That's the first term. Then I can go to the next term, which you see here, this one. This gives me a minus sign. And if we just put that one up, so let's just bring that one carefully up here. So we have plus 1 divided by 4. So let's just go back. So we see now we have a minus sign. And in this specific case, it's P and S, which are equal to I. And then Q and R are left. So that means that we would have a Q, there's a minus sign now. There's a Q, R, and I. And then when we look at the matrix element, what we're going to have is a state Q here, which we have there. And then we have the state R here. And then we have I and I, like that. And then we have an operator which goes like A of Q and A and R. If you now look at this matrix element, we know that this one, if I interchange Q and I, this gives me a minus, since these are anti-symmetrized matrix elements. So this would actually be given by minus Q of I of V of Ri. Okay, so minus minus gives me plus. Then, if you now look at what we have here, we have a label Q and a label R. This looks exactly the same, except that we have P and R, but these are just dummy variables. So we can just relabel them, and then we have two identical terms. If you then do the remaining algebra here, you will see that you will get two more terms. And these two more terms, when you add everything up, takes away this factor 1 over 4. Okay? So the final terms which you have here, this one, is actually going to give us two identical terms, except that in this case, where we take Q and S, here Q is interchanged, Q and S is a Q and S, we have Q and R. This will give us a minus sign, but then the matrix elements we get by interchanging back again is going to give us the same matrix element which we have here. So that gives us a factor of 2 with the same matrix elements, since these are anti-symmetrized matrix elements. So when I sum up everything, so I'm just going to put dots here. When we sum up everything, this will just give us 1 divided by 4 PQRS of P of V, no, sorry, P of Q of V RS. And then we have a normal ordered string of operators. And later we are going to drop this normal ordering here, because we're just going to assume that these matrix elements are given by anti-symmetrized integrals and normal ordered chains of operators. And then, since we have a factor of 4 equal matrix elements, we are going to get a sum over P and Q and I. And we're going to have a matrix or integrals. And these are anti-symmetrized integrals. And then I have an AP dagger of AQ. So this is a one-body operator. And then the final term is now going to be given by the traditional vacuum-to-vacuum expectation value of the Hamiltonian with the reference state which we have. So this will then contain Ij, V of Ij. So keep in mind that all these matrix elements are anti-symmetrized. But we often skip that unless there can be some confusion of whether we're dealing with anti-symmetrized elements or not. So this becomes interesting now, because we can now rewrite our Hamiltonian. So let's do that before we take a break. We can rewrite that in terms of a reference energy, which is nothing but the vacuum-to-vacuum or the new vacuum-to-vacuum expectation value, which is a quantity we often can calculate easily. We can even have analytical expressions for it if possible. plus a term which we're going to call f of n plus a new term. I forget to put hats on these quantities. So this f of n is now given by a one-body operator with a sum over p and q, where I have p, and then I have an integral, and we are going to write down this integral in just a moment. So this integral p f of q is equal to p of h0 of q plus a sum over the states below the Fermi level of p of I, of v, of q of I. And this is anti-symmetrized. This part here, which you see, is essential when we do Hartree-Fock theory. So the way you can think of this, if you look at this summation over I, so you're summing up over all the particle states below the Fermi level. So that means that you can think of a system like this. So this could be, again, this nucleus oxygen 16. And then you have filled in 8 protons and 8 neutrons. And then you have a bystanding particle here. So this could be oxygen 17. Or it could be atomic sodium, where we have 1 electron on top of atomic neon. That would be a model if you add 1 additional proton, obviously. So you have to add a proton for this to become atomic sodium, because atomic sodium has charge 11. So then you would take neon, atomic neon, and add 1 proton. That defines a new atomic nucleus for you. But you can think of that as almost inert in atomic physics, and you just look at the electronic degrees of freedom. So in this case, you could now think of this being a proton in a state Q here, which now sees the remaining protons and neutrons in oxygen 16. So what we are saying is that this term here, since it looks like a one-body operator, it modifies the field of this state here through the interaction with all the other particles which you have in the core. So this produces then an addition to, if you think of your particles being trapped by a harmonic oscillator, which could be this H0, you're now modifying the motion of a particle in an harmonic oscillator by including the effect of all the other particles. So it produces a new field which the particle sees. And we call this a mean field because you now sum over all the other particles. So what you see here is essential for mean field theories, which we will start with right after we've done FCI. So FCI is going to be the kind of ideal. If you can diagonalize a many-body problem, you have all the states. And then we're going to interpret many of the other theories in terms of an FCI complete calculation. So the last thing before we take a small break, and this is V of n, which is now simply 1 divided by 4. It's PQRS. And then we have the matrix element, VRS, anti-symmetrized. And this is now multiplied with the operator, which is normal ordered, with respect to the new reference state. So after the break, we are going to calculate expectation values with this new modified Hamiltonian with respect to a new vacuum state. So what we're going to do now is to calculate explicit expectation values or transition probabilities. So with this more compact form for the Hamiltonian, let's now look at some specific calculations here. So, and then we are going to look at the diagrammatic representation as well. So let's look at the first case. And now we want to calculate the transition probabilities between a one particle, one hole state and the reference vacuum state which we have chosen. So this state, just to quickly remind ourselves about that state, this is given by an A dagger and AI acting on the reference state. So when we now are setting up the expectation values or the transition matrix elements, which we are going to look at, there are going to be three terms. So if we look at the Hamiltonian, there's going to be a term from this one. There will be a contribution from this operator here. And there is obviously also going to be a constant, which we need to evaluate. So this is the Hamiltonian. And let's now set up the different components. And we are going to write this in a more, how to say, compact way, which is ready for calculations. So that means that I'm just going to look at the chain of operators which we have. So we are going to have a phi 0. And then we have this E ref, the reference energy, which is just a constant. And it should be pretty obvious and not a big surprise to see that this has to be 0. Because this is just a constant. So this has to be E ref. And then I have the overlap between the vacuum state we have chosen and this one particle, one hole state, and that has to be 0. I guess that's pretty obvious. We have assumed that if we take this determinant, so these are Slater determinants, this would typically be normalized to 1. And we have assumed that these determinants form an orthonormal basis. And that is our computational basis, these Slater determinants, based on a single particle basis. Okay? So the next term which we need to look at is this phi 0 with this term Fn, which is a one-body operator. Now, the matrix elements or the contractions which we need to look at are elements of this type, phi 0. And now I have the operator AP, AQ. So this is AQ. And then I have an A dagger and AI of phi 0. So the term which you see here, this is from the one-body operator. So I'm writing out this in a more compact way so that it's ready for looking at the possible contractions which we have. And both of these two terms are two normal order products of creation and annihilation operators. So with respect to the new vacuum, it means now if we use Wick's generalized theorem, is that we have to perform the contractions between chains of normal ordered operators. This means that in this particular case, if we now look at what we have, we can have this contraction here, and we can have this contraction here. And that's the only one which is non-zero. Would you agree upon that? Because if we now look at the contraction between this and this, that is 0. That one and that one is 0. And the only remaining ones are actually the contractions where I take this operator here with that one. So that means that Q has to be equal to A and P has to be equal to I. So that's the only possibility which gives a non-zero term. So this is delta P of I and delta Q of A. So if I then go back to the expression which I have for this operator F, it means that now we are going to get a P, which was equal to I, and a Q here, which was equal to the state A, a state below and above the Fermi level. And that translates into this set of integrals, which we have here. So let's just write it down. So this term here when we now write it out properly, this is going to be equal to I of this operator F of A, which is the same as I H0 of A. And clearly, if this single particle basis is an orthonormal basis and an eigenbasis of H0, this term, the first term, is 0. But now we're just going to leave it as it stands. And then I'm going to have a sum over J. And we're going to have matrix elements or integrals of Aj, of V, of Aj, anti-symmetrized. So that's this specific matrix element. And this is actually important because what we are doing now is a preparation for setting up the Hamiltonian matrix to be diagonalized when we do full configuration interaction theory. Because we are going to get transition probabilities or transition matrix elements, as we call them, between different orthonormal Slater determinants. Now, with this new formalism, it's actually easy to see that some terms have to be equal to 0. So if you look at what we have here, if we just pause a little bit now. Now, this is a one particle, one hole excitation, okay? So when I do that, I am actually creating a new state, which is a one particle, one hole state. Now I'm going from a one particle, one hole state here back to the reference vacuum. Now this reference vacuum has 0 particle, 0 hole excitations. So one way to label that one, so let's just go back a little bit and pause for just a moment here, phi 0. This state here is something which we will call a 0 particle, 0 hole state. We have an operator, and then we have this IA, and this is a one particle, one hole state. So in order for us to have something which is non-zero, that means that when I look at this operator here, that operator must create. So that means that when I take F of n acting on phi 0, this should create something which is a one particle, one hole multiplied with a constant. Okay, that's because it's a one body operator, right? Because what I want to, at the end, when I look at these, I want to do something which is, I want to get something which is non-zero. So I need to have on the brass side, after the operation of the operator, something which looks like what I have on the ket side. So what I'm trying to do now is to sneak in some kind of intuition about what you can expect when you're computing transition matrix elements using these new operators. Because this is going to make life much, much simpler. So when we are performing the calculations here, it means that we need at least an operator which is able to transform this state here into one particle, one hole state. And since we assume that these basis states are orthogonal to each other, it means that this state which we create must be equal to that state times some constant. And these constants are actually given by the matrix elements of the operator. So let's now look at the two-body operator. So what we are looking at now is a phi 0 of V of n. And then we have this one particle, one hole state. So it has a sum over 1 over PQRS multiplied with 1 over 4. We have the matrix elements, or the integrals as we've been calling them. And then this is now multiplied with a phi 0. And then I have the operator, and I'm leaving out this normal ordering now. So this is A of Q, of AS, of A of R. And then I have this AI, this one particle, one whole piece. So in principle, when you now look at what we have, if we take this operation here, so what we are doing here on the kets, on the brass side, is to act on the vacuum state like this. And we know now that if these states here are not states below the Fermi level, this will be 0. So these have to be states, these two here, have to be able to annihilate something which exists in here. And that means that P and Q have to be states above the Fermi level. So what this is creating for us, the operation of the operator V of n, is a two-particle, two-hole state, which I write in a sloppy way like this. Yeah?
So the P and Q has to be above the Fermi level.
Yeah.
P and Q can be creating the states which were annihilated.
Yeah, we can do that. But then that would be back to phi 0. So you could actually have, you take away two whole states, and then you bring them back. But then what that gives you is, as you say here, or phi 0. Then, if you now look at where we start with a one particle, one whole state. So the action of this operator here gives us either a two particle, two whole state, or it brings us back to this one times a constant. So what you see now is also something which you could have gotten by doing the contractions. So if you look at the contractions, suppose now that you start operating with this, so you could have this contraction here, and then you would have this one. So these are non-zero. But then you're left with the contractions within the operator itself, because these are normal order operators, and we can only take contractions between chains of normal order operators. So that means that if I try to do that one, that is 0. If I try to do any other combinations, it's going to be 0. So this operator here is something which, when you do all the contractions, is going to give you 0. But you can look at this in another way. And hopefully then, by using some intuition, you can then just see from the expression that this has to be 0 automatically. So here, you can produce now either a two-particle, two-hole state, or you can just go back to the same state. But you cannot produce a one-particle, one-hole state. So that means that when you then look at the final overlap, which you are looking at, you will not have a one-particle, one, you have a one-particle, one-hole state here, but you will not have one here. So that means that this term actually becomes equal to 0. So we just write it like that. So the final contribution for that specific transition between a one particle, one whole state and the reference state, which you've chosen. Oops. Okay. If you look at that one, so that means that phi 0 with the Hamiltonian in this case, and phi of I, and you would have gotten the same if you hadn't used the new vacuum reference state. So this is going to be equal simply to that term, which is given by I of this specific operator, F, which is given by, sorry, and if A and I are eigenbases of H0, then the first term is 0, plus a sum over J, of Ij, of V, and then we have an A of J. anti-symmetrized. Now let's take another example and see if we can use this kind of intuition we have developed and look at a two-particle, two-hole state. Like that. So clearly, one term, which is just this reference term with E0 ref, that has to be equal to 0, obviously. So let's now look at the next term, which is the one-body operator. So if we take phi 0 with f of n, and then phi I j a b, and if we look at the action of f of n on phi 0, what that can give us is, if we now look at it, so this is proportional with an AP AQ acting on phi 0. So this can produce either a one-particle, one-hole state of IA, if Q is below the Fermi level. Alternatively, it can bring us back to phi 0. Okay? Does that sound reasonable? If P and Q are below the Fermi level, then we are destroying one state, and then we are adding another particle to that state. And if P and Q are the same, then this brings us back to the same state. Or alternatively, I can make a one-particle, one-hole excitations if P and Q are different. And now you see, when you look at this now, it means that this operator here, this expectation value, is going to be proportional with some constant, or sum of our terms, multiplied with either phi 0 and phi I j a b, or new constant multiplied with phi, and now I'm going to put a k here and a c of phi I j a b. Okay? And we say again that this has to be 0, because these states are assumed to be orthogonal to each other. And one is a two-particle, so this is a two-particle, two-hole state. This is a one-particle, one-hole, and this is a two-particle, two-hole state. And we have by definition assumed that the basis we start with is an orthogonal and normally normalized basis as well. So this has to be 0. So the one-body operator is just giving us 0. And we can actually see that immediately without doing any calculations. And when you bring in a diagrammatic way of thinking, you can actually just draw diagrams of the operators. And then from those, you can see which terms should be 0 and which are not. So that gives a very powerful way of actually performing the calculations, instead of just going through all the gritty, nitty details. So that means that most likely, there's only one term which gives us something different from 0. So let's take a look at that one. So if we now look at V of n acting on phi 0, this is something which we agreed upon can give us either a constant times phi 0, or it can give us a new constant times a state, which I'm just going to label as a KL and CD. So we can either get a two-particle, two-hole state, or a zero-particle, zero-hole state. So that means that this is something which now can give us a term which is non-zero. And that would come from this term which we see here now. So let's look at the contractions which we get. So now I'm just going to only set up the contractions. So what we are going to look at is a contribution of this type here, where we have AP, AQ, AS, AR, and then I have an AA of AB, and then I have an AJ, AI acting on the vacuum state. Now here, the only contractions which are non-zero are obviously the set of contractions where I now take these two operators with these two. So I can have this contraction here and that one. Or I can have between this set here, this one with that one. That will give me a minus sign because I have to interchange two operators. And then the other possibility is now this chain of operators here, which now is getting contracted with this one. So that means that this one has to go here, and that one has to go there. Or alternatively, I can now look at this one going to that one, and no, sorry, that was wrong. So I can have this one going to that, and this one going to that. So that will give me a minus sign. So I will have 4 different Kronecker deltas. I have 1 divided by 4 in front of the operator. And then since these matrix elements are anti-symmetrized, this will just give me a set of 4 contributions, which are all the same. So when I sum up everything here, you will see now that if I take the first one, so suppose now I take this term here, and I match that one with this one, I'm going to get, so if we take these 2 sets of contractions, I'm going to have a delta P of I, a delta Q of J, multiplied with a delta R of A, and a delta S of B. And that will give me an integral which goes like IJ V AB anti-symmetrized. The other ones are going to give us 4 similar terms. And since we are dealing with these anti-symmetrized elements, then when I calculate and add them all up, then this expectation value, this transition of matrix element or element, is simply going to be given by IJ V AB anti-symmetrized. And this is what you found back in week 37 when you used the Condon-Slater rules to calculate transitions between states where you had 2 different single particle states in the bra state and the ket state. Now, one thing, if we now stay with a one-body operator, which also shouldn't come as a surprise, is that if I now try to take the transition between a free particle free hole state and a 2 particle, no, 0 particle 0 hole state, and this is at most a 2-body operator, what should I get in this case? If you think back to the Condon-Slater rules. So here I will have 3 states, single particle states, which are different from this one. So there are 3 single particle states. And I have a 2-body operator. So if you think back to that exercise in week 37, when we looked at the Condon-Slater rule, what happened if you had more than 2 particle states which were different in the ket side compared with the bra side?
0?
Yeah, exactly 0. So that means that in general, what we are going to have is if I now write this as an n hole and n particle excitation, this is 0 if n is larger than 2. So if you have states which differ more than 2 single particle states on the brass side and the Ket side of such a transition element, that will always be 0 if the operator is at most a 2-body. You can complicate life here by saying that the operator is a 3-body operator. That clearly opens up many more possibilities and makes life much more difficult for people who want to do many-body physics, because we are normally hoping that 3-body correlations and 3-body transition elements are as close to 0 as they can be, or preferentially 0. Okay? So this becomes also very important when we are setting up the Hamiltonian matrix to diagonalize, because that means that your Hamiltonian matrix is going to be a sparse matrix. So if you have, let's say, 100 particles, you can have 100 particles and 100 hole excitations you can make in total, which means that there will only be contribution to a Hamiltonian matrix of this type, 1 particle, 1 hole, and 0 particle, 0 hole. And all the other elements will be 0. So in general, when you're setting up the problem in this way, and this is one of the reasons why I'm doing this, is actually that is a way which simplifies the way we think of a full configuration interaction calculation and the setup of the basis states, and the way we can simply say that this matrix element has to be 0 without performing any calculation. So in a bitwise representation, what you would do then, when you're calculating these elements, and in a typical large-scale diagonalization approach, you will calculate these elements, the action of H on a state, on the fly. So what you do then is that you would compare bits. So you would represent a state as a collection of bits, 1s and 0s. And then when H acts on this one, that produces a new state, which is a new collection of bits. And the thing you do then is simply to compare this word with that word. That's the way you would store them. And if they differ by more than 1 bit, then that has to be 0. Okay? That's a very efficient way by which you would actually encode this information. We are coming back to this a little bit later. Now, what we're going to do next now is actually to look at the diagrammatic representation. So let's introduce that before we do some more calculations, because that's something which gives us a very compact way of representing many of these transition elements or expectation values. Now, the new thing is that we want to include whole states. So we have defined a particle state as an upgoing arrow. So and now we have this states A, and this would typically be labeled like this. This is a state A. And you remember that when we looked at a specific 1-body matrix element, or just a 1-body term, this is something which we would rewrite in a diagrammatic way as an interaction term here. So this represents H0, or it could be any type of 1-body operator. And then we have an incoming state B, and we have an outgoing state A. So this is the case when we just had particle states, and we haven't defined any kind of reference vacuum state. Furthermore, when we looked at something like this, A, B, or B, and C, D, and now we're just looking at the direct element, so this is not an anti-symmetrized element, we would write this in a diagrammatic way in terms of such a diagram like this one. So this would be C. So of the incoming state, we have the 1 to the left, which stands in the diagram to the left, and then D to the right. and similarly with A and B here. And this dotted lines represents now the interaction or just the two-body operator. Okay. So what we need to do now is to have a different labeling or different notation for whole states. And a whole state, and this is very much borrowed from antiparticles in particle physics. So a whole state, which we now label with an I here, is now given by a downgoing arrow. So let's see how this translates into a diagram. Now, suppose we don't look at the particle whole formalism. So think of I and A as particle states. Yeah?
Whole state now, because
yeah,
there was some confusion with the main whole state.
Yeah.
Is this an actual whole you're talking about, or are you talking about states under the Fermi level?
State under the Fermi level. So you create, but you create like later we are going to create one particle, one whole excitations, right? So that means that there is actually a state which has been removed below the Fermi level. So in a way, what you're doing here, when you look at this case here, if you now want to be a little bit more specific, if we now look at this as states without a reference vacuum, the traditional vacuum state, which we have the zero, the true vacuum, this will be an AI like this. And if we now only have one particle, suppose you have only one particle here, this means that you would be in a state A here. And then after this action of the operator, you're then going into a state I. So that means that you would leave out of this state and you would fill in this state. That's the physical interpretation of that process with the true vacuum state. Now, when we now have a whole state, the way we are going to represent that is simply by bending the line here. So just think of this diagram like us bending it this specific way. So if you bend I up again, it will be a diagram with a true vacuum. But now it's representing what we will call a one particle, one hole excitation. Okay. So in this quasi-particle picture, this now represents a one particle, one hole excitation, or actually a one particle, one hole de-excitation, which is a better wording. So if I have this element on the other hand, of F, of I, if I look at that one, this operator, and now I have to be a little bit careful because here I looked only at H0, but now I need to include this two-body term. So let's just remind ourselves of that. So this contains now a sum over J of A, J, of V, I, J. So let's write it fully out here. Plus, actually minus AJ of V, JI, plus this one body term, which is A of H0 of I. Now, this specific term, which we see here, that one, if we now use the rules which we had, would be given by this outgoing particle state, A. And in principle, we have a whole state coming in, but then we bend it up so that it points downwards. So this is an I here. This is also a one particle, one hole state, but now this is something we can think of as a one particle, one hole excitation. And you can see that from the term here, we have a one particle state, and then we excite this one up to, we have a one so-called one hole state, a state below the Fermi level. And then we promote this one up to a single particle state above the Fermi level. So we would call this a one particle, one hole excitation. Now let's now look at this term here. Let's just take this one. So that specific term, J, and the way we wrote them previously would be something like this in a diagrammatic form for the true vacuum. So we have an A going out, we have a J going out, like this, if these are particle states. And then I have an I coming in and a J coming in. If I now introduce this as whole states, this becomes equal, so I have a sum over J, and now I have this particle state I have the whole state, the particle state A, and whole state I. Sometimes I make this AI, or becomes a mess. And then I would draw this as a whole state, the state J, like that. Now, this notation is a little bit clumsy because I have to keep the summation sign. So what is common to do now is that when I have a whole line, which gets summed up over all the possible whole states, I would rewrite this in terms of a closed loop. And this will become this diagram of A of I here. So this is a kind of more compact notation which we end up using. Now, I will also have an exchange term in this specific case, which comes from this term which we have here. And if we are now going to write this in terms of a particle picture, so let's just look at it the way we did previously. So we have a sum over AJ of V and JI. So when we wrote this one previously, this is something which we wrote as a minus, and then we have this summation over J. Actually, we just put a plus sign. We have the interaction here. So we have an A going out. And now we have a state J, which leaves here. That's the state to the right. But then we have a state I, which comes in here, and a state J, which goes in here. Now, in the particle hole formalism, then we have to bend these arrows for the whole states and just turn them downwards, which means that we would write this one as a plus. So we leave out the minus sign because when we are writing off the analytical expressions, which is this one, then the two crossing fermion lines give rise to a minus sign. So crossing fermion sign, remember that gives rise to a minus sign. Now, in the particle formalism, this is something, or in the whole formalism, this is something which we would redraw like this. So we would now have a state J, which comes in here, as you can see from that one. And then, so this is an I, and this is a J. And then I have a whole state I coming in, and a whole state J leaving here. So the diagram which you see now can be twisted into a diagram in a particle hole formalism. And I would simply rewrite this one in the following way. So I have a particle state here, and this whole line which I'm summing over is something I would draw like this. And then I would then have a whole state coming in here, this I state here. So that would be the exchange diagram of that one. So it is irrelevant whether you draw this one this specific way or whether you draw it this way. Now, what is common then is to add a new definition to the diagram rules. And this is something which we will pick up tomorrow, because we can then set up new rules here which follow the contractions. And in this case, we are going to have an internal whole line, and that will give rise to a sign -1 due to the contractions. But then there is a loop, which is also counted as a quantity giving rise to a minus sign. So we have minus for one internal whole line and minus for one loop, which gives plus. In this case, a loop means that the line starts at the same vertex and ends at the same vertex. And in this particular case here, a vertex is actually given by this point here. So this ends at another one. And you can see that immediately when you open it up here, that this corresponds to actually this diagram here. And that is not, this quantity here is then not counted as a loop. You have a whole line, you give rise to -1 and no loops. So you have simply a minus sign here. So this is the kind of compact notation which we end up with in the particle hole formalism. And tomorrow we're going to look at how we can actually both use these diagrams and see that from the diagrams we can say which transition probabilities will have to be 0 and not.